Welcome back, everyone, to the next experiment. So, in this series, we're having a chat with a range of DOE enthusiasts, experts, evangelists, hearing about their personal stories and their journeys with multidimensional experiments, the trials, the triumphs, how they've used it, what they see for the future. And I'm really happy that for this episode, we've got my colleague, Owen Jonathan. I've known him for a few years now. I was actually involved in recruiting him as an intern, and now he works as one of our sales engineers at Jump. And I really wanted to get him because he's a lot younger than me. He's a lot newer to all this. It's less of a distant memory for him, his first exposure to design of experiments. So yeah, interested to hear what you thought about this episode, Marcus.
Yeah, so it was a great conversation, wasn't it? And we got to explore about, what it is like for somebody who actually encounters DOE quite early in their career and reflecting on the differences there between what he experienced and maybe what the majority of people still experience. I think in a lot of ways it's quite lucky to come across things fairly early and then actually got the bug for it, it seems, pretty quickly and understood it, just made sense to him. And very quickly then looked for a job that allowed him to pursue this as like a central part of his career, right?
Yeah, but he was surprised, having been exposed to it fairly early, that it didn't progress as he was expecting through his undergraduate studies and his master's degree. That was really
Right.
interesting.
Right. So maybe he did have a bit more of an experience of the norm as well, alongside that early exposure. I remember we were talking a bit about obviously the complexity of biology and how it's important to be using multifactorial methods within biology. And we're also talking about like how we can try and communicate to people about this quite abstract concept of DOE multifactorial experiments and how storytelling is really important. And I know you use storytelling a fair bit, and we spoke about that.
Yeah, it's one of the things I've seen Owen does really, really well. Is he has a great presentation style and makes it very accessible and fun, and tells great stories to make that connection with scientists who are, finding it a little bit maybe threatening, a bit overwhelming, this idea that they need to rethink how they do experiments.
And then I think, like looking at obviously how DOE is introduced to people and that kind of thing was really interesting. But then toward the end as well, we also just ventured a little bit into what the future of, experimental design might look like, and, exploring a little bit about where Bayesian optimization might be used as complementary to DOE and that kind of thing. And I thought that was really interesting, especially because this isn't an area that I've looked into in a lot of detail yet. So it was great to explore that a bit.
Yeah, absolutely. It's a hot topic for everyone at Jump at the moment, for sure. So, yeah, I hope everybody enjoys this episode. So, Owen Jonathan, welcome to the next experiment. I know you have been working with you for a few years now. I think I was even involved in interviewing you as an intern a few years back.
Yes.
But for the benefit of Marcus and for our listeners, would you care to just introduce yourself?
Yeah, so hi everyone. I'm Owen. I'm based in the UK. I'm originally from Indonesia. I did my studies here in the UK, focusing on biotechnology, and then I did my master's on synthetic biology in Imperial College London.
Nice.
Cool. Yeah, thanks, Owen, and really nice to meet you. Thanks for joining us on the podcast. As you know, this is a podcast where we're talking to all sorts of DOE enthusiasts about, what got them into DOE and that kind of thing. So, maybe we could just kick off with that. When did you first hear about DOE? What was the context?
Yeah, so I was an undergraduate when I first heard about it, and it was just after my first year, and I was involved in this competition. It was in the summer. It's called iGEM, which stands for Internationally Genetic Engineered Machine, I think. So I was in the University of Manchester at that time, and our team were composed of 9 students. We did our work in the MIB, and the first time I heard about DOE was from a PhD candidate who was supporting our team at that time. Someone that you might know, Marcus. His name is Ross Kent.
Oh, no way.
Yeah. So he was the first one who kind of like introduced us to DOE as a kind of a way to do experimentation. I was very intrigued. I was a first year, just did my first year, so I was kind of like new and kind of didn't really know what's out there. So it was quite interesting to learn at that start.
No, that's fascinating. I think it's one of the features of our kind of DOE community, if you like, that there's it's pretty tight a lot of the time, and
Yeah.
often different people know each other through various different connections. Obviously, something we're trying to expand, right? So
Yeah.
hopefully, over the years, then it's going to be a lot harder to have those connections come back around again. Um, so when you first heard about it, you say you were kind of intrigued. You know, what did you find it difficult to kind of get your head around the concepts, or did you find it relatively easy? Were there any kind of major hang-ups that you had, that you had to try and get past to try and wrap your head around this way of working?
I think because I was a first year, I was a bit lucky. I came in with an open mind. I didn't know what I didn't know.
Right.
So I thought, okay, that seems cool. Trying to strategize your experimentation. It feels obvious. And it fits with the whole, synthetic biology aspect of like trying to standardize biology, trying to make biology reproducible, predictable. That was kind of the whole gist of synthetic biology. So I felt like it was okay. That seems to be a very natural thing that I'm probably going to learn. And it turns out that I never learned it in my studies at all, which was quite surprising to me.
Right. So it was later on then where you actually became more familiar with DOE and how it's really applied in biology in the commercial world.
Yeah, so when I did that project, I did, I think, I helped out with the round of DOE, and I thought, okay, cool, we moved on. I'll probably learn a bit more about it in my undergraduate. Never came across about it. No one never ever
Right.
mentioned it, and I thought, okay, maybe it's something that you learn when, at a higher level. So I did my master's in synthetic biology, thinking, okay, now's the time where I finally will learn it, and it never popped up either. So I thought, okay, something is a bit wrong here because I feel like it's such a natural thing to learn, especially within the field. And yeah, I never came across it. And neither, I was working in a lab with PhD students, and neither of them have heard it either. So I thought, okay, maybe I should look elsewhere to learn about this. And that's when I found this internship from Jump on
Right.
DOE in biotech. It was sent by my professor, so I thought this seems like a good opportunity. So I just went in right ahead.
Huh. Yeah, I mean, it's kind of a bit depressing, but not really all that surprising that you didn't actually get a chance to learn about it within your studies. It is getting better, I think, but I think overall it's still the case where, the vast majority of courses, and frankly, the vast majority of people teaching those courses don't really think of it as a subject that
Yeah.
is really important. Um, but I mean, you could argue, obviously, that given the complexities of biology, then it's needed more here than anywhere. Do you have kind of a sense of like those particular challenges in biology and why maybe we find it so suited to kind of a multifactorial approach?
Yeah, definitely. Biological space is, we can say it's a bit complex. A lot of parts are interchanging one another. And we do this one factor at a time approach because I think it's just intuitive. It's easy for us to learn. We see a graph, we change one thing, we see an increase, like, okay, that's the cause of it. It just makes sense. But then when we really understand how complex biology is, we need better tools to definitely understand that complexity. And even though our human brains can't really understand what's happening with, a DOE run, we've got powerful software that can understand that for us, and we can build models that really uncover these complex interactions in a way that even anyone can really understand how things behave.
Right.
Hmm. Yeah. I The sense I got was that DOE is more well known in biology and it's more prevalent in at least postgraduate education in biology. So it's kind of disappointing to hear that that isn't the case. It's definitely not the case in chemistry where I grew up in my scientific education.
I think it's
But
pretty
yeah, so
patchy, Bill, from what I can see.
mhm.
It kind of, there are some places where, they're starting to see, but I think it's that same kind of pattern you see anywhere. If someone has been exposed to it, tried it, got, hooked on it, then they're going to try and push it in the course that they're involved in, at the institution that they lecture at or whatever. And if they haven't, then it remains, it seems to be a pretty binary thing, right? Either you know about it or you don't. And if you don't,
Mhm.
then how would you know to put it on the course, right?
Yeah,
Yeah.
yeah.
One funny thing about that, actually, like towards the end of my internship, I ended up doing like a training on DOE to my classmates. So
Oh,
I
cool.
thought that's a very full circle moment there.
This is be the solution you want to see, right?
Yeah, yeah. Like I thought I was gonna learn a bit, but I ended up kind of quote unquote
Well,
teaching it in a
you know,
way.
best way of learning, right? You
Yeah,
have to know what you're talking about if you're going to train
that's true.
people on it, you know.
Yeah.
So you'd
So
had a bit of experience of doing DOE in that iGEM
hmm
competition, and then several years where it didn't happen at all. So how did it go? What was your first steps in learning more about DOE when you came to Jump as an intern?
So the STIPS module from Jump was very helpful to kind of just get me started, not just on DOE, but just basic stats and how to apply stats on your work. I think that's one area where we were never really taught in university as well. We learn like do this if it's t-test, ANOVA. Like, it's more like a checkbox on how you approach
Mm-hmm.
statistics rather than seeing it at a holistic level. So learning that those modules actually gave kind of a grounded more understanding of where we apply stats and why we're doing it. It's not just a checkbox exercise. So I think that was the first big, and to also see how DOE kind of fits into that picture, which is quite useful as well.
and then what have you seen since then? I mean, obviously it's one thing learning the theory, but it's kind of another than actually seeing it in practice or helping people through things or seeing case studies that come out. You know,
Mhm.
have you seen particular instances now where you're excited about like how it has been able to give particular insights in biological systems?
Yeah, I think it's the result just speaks for themselves, how much efficient people can be, how much understanding they can really get from that. And that's the thing that really draws people in. And I think we see this a lot in industry, when you've got a time pressure on, you've got certain budgets, limitations, and you're kind of forced to do DOE because, you don't have 4 years to like understand that whole process and like a PhD, and then they immediately get bought right away. But there's no once you've kind of learned that in industry, for some reason, it kind of just goes one way. It never goes back to the academia curriculum. So,
Right.
yeah.
Right. Yeah. I don't know whether it's because Dewey's classically been associated with kind of more industrial process optimization. And so
Mm-hmm.
then, people tend to put it in that kind of bucket. I mean, certainly those academic departments that I've seen, teaching it a lot more are often more at that kind of applied end to do with,
Right.
scale up of processes or whatever. Um, and, I think there is still a major realization that has to happen in biology overall that, look, we're
Mm-hmm.
working with this big, complex, interconnected system and really there's only one way to look at that, and until kind of we get past that threshold, which is probably going to take quite a long time to
Yeah.
happen, that
Yeah.
that's when I think we're going to see it pervasive across biology, and just a natural prerequisite to a career of doing biological
hmm
investigations in the lab, I think. um, yeah, it's we got a fair way to go, but this is why we do things like this, right?
Yeah.
In order to try and talk about it more and understand what the opportunities and pitfalls are. I mean, what do you think? I mean, from your um, seat there in Jump, obviously you're interacting with people from all over the place,
Mm-hmm.
and what do you see as the best way that we can use to get more people using DOE? I mean, we've obviously got a vested interest in this as two companies that supply tools for doing DOE. So you might say that oh, hang on a second, this isn't completely impartial, but at the same time, there are a lot of results that just speak for themselves.
hmm
But like it somehow we need to be getting that out more. I mean, how do you think we can go about doing that? How do you think we can convince people that this is the way to go?
That's always the big question, is it? How do you challenge people over? I think we start with the people who are new coming in because, there's some people working in these companies for decades and decades and they've got a way to do things. And those are the people that typically are like blockers that are very difficult to change their minds on. And it's really the, new people coming in with a fresh, open mind that's willing to like learn new things. That's where we see a lot of like the push come from. So, for example, there might be a new person just graduate their PhD, join a new company as an associate scientist or something. They figured out DOE because they were forced to kind of learn it because of constraints, and so they were trying to figure a way out, and that was the result that they found. They went through it, found some success, and then they become that internal advocate for DOE within their company. So we see this quite happen quite a lot of time actually, where it's the newer ones who are kind of trying new things out and really trying to push that towards the older management.
Yeah. And one of the things I've seen from you, Owen, that you're particularly good at is storytelling around DOE and stats more generally. I'd already told Marcus the story of Dr. Stevie and Dr. Charlie in an earlier episode. That's one of my favorite stories. How do you use storytelling as part of this to get more people using DOE?
Yeah, I think storytelling is very, very powerful with this kind of thing. So when people talk about stats, they immediately go like, okay, it's a lot of numbers. I study biology not to look at math. That's not what I want. And really trying to like recontextualize that in a story is can be a very powerful thing. And this is one approach that I'm trying to do, and I'm still testing things out. And so far, I think it's been going quite well. Dr. Stevie and Dr. Charlie always gets a lot of good responses from people. So I try to create something else along those lines as well, and it's been pretty good. It's been pretty good.
I think we're getting a growing number of stories sort of out
Yeah.
there as well, right? Various different people's personal experience of doing this kind of thing, and I think it's very important as well to remember back to our own kind of journeys into DOE and the hang-ups that we had at those times and what we had to overcome in order to get to the point of kind of deep conviction that we all carry now. And I think it's also important not just to talk about like the facts and this experiment would have taken this amount of time
Mhm.
and now took this much less time, but also to talk about the emotions of stuff. And I don't think that as scientists we're particularly used to doing that, but there's a real angst involved in a lot of biological experimentation because you expect it to fail a lot. And so for me there was a huge release and a feeling of, oh wow, this is amazing, real excitement, which we just don't talk about that much, about like, oh, hang on a second, I've now got a framework that actually allows me to make definitive progress. And I think this is why we all turn into such zealots about the method, is because once you've actually seen it in action, particularly in biology, which can be such a really tough place to make any progress at all, then yeah, I mean, it's you don't go back after that, right? It's
Yeah.
it's quite an intoxicating feeling, and like talking about those kind of very real emotions, I think is part of the story, right?
Well,
We're not writing
yeah.
a scientific paper here.
Yeah.
We're trying to kind of tell a story. We're trying to convey what we've experienced to other people, not just the data. Although the data is pretty important as well, right?
Yeah, I agree. I think I maybe read or heard about it somewhere in like psychology or economics, where we as humans we often think that we're like logical creatures, but it's really our emotions that force us to make decisions. So yeah, I agree completely, and I think that's where storytelling can help play. We focus on the pain points and what people get out of it, and how they might relate to their self like personally. I think that could be one way as well.
Yeah,
And do it in a way that's fun and not threatening. I
Mm.
think statistics can sometimes feel like it's a punishment,
or that
and
it's telling
we
you
don't
off,
want that.
right? It's
Yeah,
like, oh
yeah,
no, you shouldn't be doing that way. That way's wrong. It feels quite threatening, doesn't it? It's kind of
yeah. And that the famous quote from Fisher about I can tell you what the experiment died of. Kind of, I've always thought that was a bit of a smug and not necessarily helpful kind of attitude to take towards supporting scientists in their experimental endeavors.
yes,
Um,
it's a certain
but
area of
yeah,
superiority there, isn't
Yeah.
it? It wasn't the
yeah,
most problematic thing about Fisher, but maybe we won't go
no,
there.
this is true. Yeah.
um, so, what have you found hardest then about getting people along that road, right? Kind of obviously there's a lot of mental hang-ups that we've already kind of
Mhm.
alluded to, but like as people are going on that journey, like how do you get them to that first experiment, right, where they've actually run something and they've seen the data and they're because that's the moment of watershed for me, like that's the epiphany moment, is when people have actually run that first experiment.
Typically, I found that people are, well, talking to the ones who are more open-minded, it typically is a bit easier to get them started, but it's to get them kind of hooked is can be a bit of a challenge, especially when they've done a few experiments and like the experiments failed and they think it's a waste of time, and really trying to like tell them to keep holding on, that is still useful information. You can still get out something from it, and maybe you didn't plan it quite well with the factor ranges. Maybe it was too wide, it was too narrow, and really
Right.
guiding people in like the concrete steps on each of the parts.
Right.
Mm-hmm. What are some of the, particularly in biology, I don't really know what it's like to try and run experiments in the world of biology, but the sense I get are there's some very significant and unique and important practical challenges to actually doing experiments in the lab in the world of biology. What are the big things that you think maybe are barriers, and maybe where, as software and statistical method providers, we can actually improve matters, help more scientists to embrace this?
I think in the past, a lot of biology was done like very manually. And it has only been recently where we've got these robots that can run like assay plates many, many times in an accurate fashion. I remember staying in the lab for like 2 hours just pipetting each well individually, trying to be a robot. And I think that's one of the practical limitations. It is a lot of like laborious process that we have to go through, especially with the runs. It's not just a simple matter of clicking a button, switching things off, turning the dial. It's really manual handling. For the project that I did, for example, in iGEM, that was a bit of a unique case because the factors that we were working with were like gene constructs, and so each individual run was one plasmid that we have to like construct, transform, and clone, and that's just for one, and we've got to repeat that 12 times, which is, it can take weeks to just do a 12 run design. And we did like 2 rounds, and that took us the whole summer to do.
Yeah.
Yeah.
I think
Marcus is nodding his head there because he knows what that all that means. I don't have a clue really. Why does that take so long? What's actually involved?
Well, I mean, it's got better over the years, but typically the process of cloning, which is the
Yeah.
odd name that we use within biology for stitching together a piece of DNA that you then want to put into a living organism, is fraught, right? And it fails pretty often. I mean, at Synthase, actually, we did quite a lot of optimization on that process itself using DOE, right? So then, we made it a non-problem using DOE, so you can. It is kind of building like a tool stack within the lab
Yes.
of all
Yeah.
the different methods and things, and then you can reach higher to ever more ambitious experiments. And what I kind of think of this as is like factor access, right? How do you actually be able to get to some factors so that you can change them and so that you can investigate them as part of your overall design space? And yeah, genetic factors are some of the hardest ones
Yeah.
to change. And they're also like, these are, it's not easy to necessarily know how to treat a genetic factor.
Yeah.
Do you just treat it as a categoric thing? Or, some of them though have strengths associated with them, right? So there's you can tune up how strongly a gene is used within a cell, right? And there are bits of genetics that allow you to do that tuning. So then you'd think, okay, well, is this then a discrete numeric factor, or is it a continuous factor? So there's all sorts of things. And, as I've said to you many times before, Phil, I feel like we're only just scratching the surface in terms of application of these kind of methods to biology. And it's pretty exciting to see where it might go.
Yeah, definitely. Yeah.
I feel bad for Owen though, that because he went right in the deep end there. I think we have to have a word with Ross, right? Right in the deep end of like some of the hardest factors to change, and then only 2 iterations in the summer is pretty tough going, right?
Yeah, it was quite cool though, because I didn't realize that this was not something people do on like on a typical basis, that this was quite cutting edge in a way. Like, oh, okay.
Yeah. No, there is still, unfortunately, there's a relative paucity of high dimensional experiments that are actually out in the literature for biology. And I mean, this is obviously part of the problem. And again, they tend to be on the process development side of things. And so it's quite exciting that actually within kind of this area of synthetic biology, which has kind of this aim of engineering biology, making it a hell of a lot more predictable, that naturally, I mean, you said it earlier, Owen, it has kind of an affinity, that kind of philosophy of going about it. We're not just observing a system now with tweaks, we're actually looking to engineer it predictably, which means that then, it's a maybe a field that's that much more kind of prone to thinking about things in the way that we do, from multifactorial experimentation perspective, right?
Yeah. So, I mean, that experiment sounds like it was foundational in your journey of DOE. Are there any other ones that you can think of that you've either been involved in personally or you've seen from customers that you've been supporting that you've really learned a lot from? Maybe some really big successes or even some spectacular failures that you've really learned a lot from.
I really like, well, I didn't really work with him in a way, but we did a joint presentation. It's Alex Rimmer from, I don't know where he is now, but he used to be in a company called Uncommon, and I think he worked with Synthase for this project, where he did DOE for growth media to grow some cells. I
Right.
think it was like pork cells, and he was able to get like a lot of efficiency out in a small number of time, where in comparison to that OFAT approach. So that was a big breakthrough for him personally, and we talked about it as well when we met about it.
Yeah, I think that, particularly, I know Alex well, and he's yeah, he's another example of one of these kind of scientist who at the time was relatively early in his career, very keen to be using new methods, happy to, really go out there. I think, that particular experiment he did, I think it was something like 420 runs, which for his particular system was, really quite challenging,
Hmm.
and looking at like 22 factors simultaneously. So this is
Wow.
a really big scope experiment. And it was interesting to see because, the complexities of optimizing media for particular cell lines is huge,
Hmm.
right? And so it was interesting to see then how an expert, cell biologist then thought about that overall space and narrowed it down, right, to 22
Yeah.
factors, and then successfully managed to optimize on those. Yeah, getting some quite dramatic results. Um, it's not always the case with cell-based systems, I have to say. Like,
Yeah.
I've seen some particularly ambitious ones, where they've been looking at putting lots of different cell types together. So you're kind of compounding complexity with more complexity, and this is kind of the sort of experiment which I think is quite desirable in some areas. But even with the power of automated multi-dimensional experiments that we do now, there's still further to go. Right.
Yeah, I feel like there's always a degree of abstraction when trying to apply DOE to biology, because, as you said, biology can be very, very complex, and we kind of have to narrow it down to something that can be done. Um,
Right.
Even with genetic constructs, we've got, yes, the tuning that we can change increase the strength and reduce it. But then there's also other genetic parts that we could potentially run the DOE on, but we just didn't because that would increase the complexity by a lot. So there's
Yeah.
always feels like a degree of abstraction that we always have to apply.
Yeah, I mean, if you think of, I mean, even a short gene, a very short gene, say, I
Mhm.
don't know, 300 base pairs or something like that, then you could think of that as 300 factors with
Yeah.
four categoric variables, right? You could think of it that way. Now, obviously, we do have to abstract to get away from such a granular thing. And I don't really know how helpful that representation would be when then trying to model it, because you're going to end up with a hugely spiky
Mm.
landscape across untold numbers of categoric factors if you were to do that. Um, so I think it is a real challenge thinking about the best ways of navigating these, not just not just complex in kind of the number of factors and the interconnectedness of those factors, but also in terms of the potential smoothness of the landscape that we're exploring.
Hmm.
Instead of like, the nice rolling hills that you could imagine in, some kind of process development of, oh, I tweak temperature from, 35 degrees to 35.5, you'd expect that to have an incremental change, not a dramatic change in most instances, right? But I think there's a hell of a lot of biology that, you know, you're you've got cliff edges all around you, right? Or maybe you're just standing on a single spire of rock with uncertain where to step next. And I think there's we've spoken about now we have all these runs in biology, right? You've spoken about automation and this kind of thing. We've spoken briefly about Alex's work at Uncommon. So we are lifting the ceiling, if you like. We're raising the ceiling on what's possible. But I don't think we're going to run out of challenges anytime soon, to be honest.
No, there's so much to go at, isn't there? I mean, I think it's going to be a case of just trying more stuff, trying to be more ambitious incrementally and learning from it, and encouraging more and more people to try and be more ambitious about it. And, I think we need to learn also as methods providers, the statistician developers and software developers also need to be right in the thick of this, really getting their hands dirty, metaphorically speaking, with biology and really learning what the challenges are. I guess you don't want dirty hands in the world of biology, right? That's a no, contamination free, but
not so much.
You know what I mean? So I know, Owen, you've been recently, everybody at Jump has been getting very excited about Bayesian optimization. And that's something you've been talking about quite a bit. I don't know. I'm just going to ask you, what do you think is the future of DOE in biology? And maybe I'm leading you a little bit. Is Bayesian optimization and methods like that part of the future of DOE in biology?
Yeah, I definitely think so. At least I had just got out of a call today, actually, where it's a CRO company, so they work with a lot of other pharmaceutical companies, and they said that they developed their own Bayesian optimization solution because a lot of pharmaceutical companies were looking into it. So that seems to be like the area where people are going to find a faster way to get to where they are, to go through this complexity, kind of like a shortcut in a way to really understand and get to the goals that they've set for themselves.
Mm-hmm. Maybe you should just briefly try and explain what Bayesian optimization is and how that differs from what we might think of as DOE currently.
Yeah, so I think the difference lies in the focus. For DOE, for example, when we try to kind of create an experimental design, the focus is a lot more on the factors, where you're kind of exploring the factor region space. And as Marcus said, in biology, that's where we put a lot of our thinking, trying to figure out what are the factors, how do they change, are they continuous or categorical, and so forth. So it really is just on the factors itself. Whether or not your response is trying to maximize or minimize doesn't really have any impact to the design at all. In Bayesian optimization, however, the goal that you've set for your response is part of that, weights to figure out the next experiment you do. So unlike a DOE where you need to say run 16 or 32 runs at a time, Bayesian optimization does it a bit more iteratively. So it learns from the, say, one or two experiments that you've done, and then looking at your factors, ranges, and your response and some uncertainty within the region, it then gives you, try this one next. And it does that iteratively until you've meet your goal. And we've seen that it's able to cut down experiment time for a bit, and with the more focus on the response and meeting your goal rather than understanding.
And it potentially also seems like it's more appealing to scientists in the way that they just want to get in there and start trying stuff, right? It's not this, you have to do these 16, 32, 64, however many runs before you can learn anything. It's more sequential. It's more like a rapid feedback. So you can go into the lab, try something, then it guides you to what to try next, and you can try again. Maybe it doesn't lend itself as well to these highly parallelized automated systems.
It's a really interesting one, isn't it? Because what I'm immediately thinking about is that there are some biological problems that you might have where, you can set up the runs pretty rapidly, you can get data back pretty rapidly, and you can iterate pretty rapidly. So I could imagine then that kind of approach of kind of iteratively exploring and getting better definition about those parts of the space where you have least knowledge, and then exploiting those really, exciting parts of the space that you uncover along the way. I think that could be a really interesting way of working in those systems. And then by contrast, though, you also have other biological systems that might take the experiment itself might take 6 weeks of cell growth, right, or something like that, right? And then and then if we think back to the origins of DOE, right, back to Fisher again, they were looking at crop growth, which is very much analogous to that, right? You essentially get one experimental round per year. And at that time, I mean, these days they go northern hemisphere, southern hemisphere, so they get two. But it's then much more of an emphasis on how much can we learn from the breadth of an experiment, parallelized as much as possible. And I think this is at least then we have a bit of a handle on thinking about, okay, well, which might we choose? We've got these two different things in our toolbox, and when you're first then looking at a biological problem, you could be thinking about is it something that we can iterate fast on? How much does it cost to iterate? How much time do we have for the project? And then other human factors, like you were talking about, Phil. It's like, is this actually a little bit more understandable or accessible than, us just going in and saying, hey, Alex, do a 420 run design, right? It takes maybe quite a special person to, immediately jump in with both feet when you're presented with that as your next experimental option, right?
Yeah. Yeah, and maybe it's a gateway into the idea of multifactorial exploration, exploring these multidimensional hyperspaces, which feels kind of unnatural. So maybe this is a more accessible way into that.
Yeah, I think that's certainly a hang up, isn't it? It's a way of, you have to change from looking at the world as a relatively understandable causal thing, which in most of our day-to-day lives, there's a lot of stuff that is quite causal. If I drop something, it will drop. If I press the accelerator on my car, hopefully it's going to go faster. But actually then shifting to something which is a kind of more nuanced view, perhaps, of the biological systems we're looking at, where things just don't have such simple causality, and that it is high dimensional. And I think once you're there, can provide a much better understanding of not just biology, but a hell of a lot of stuff that goes on in the world. But it's a bit of a leap, isn't it, to get there in the first place? So yeah, maybe beige, we can use this as the gateway drug. I think that's a term you used, wasn't it, Phil?
I didn't use that. No, I don't particularly like that term. But if you want to use it, yeah, go ahead.
I'm joking. So, is this something that you see as a feasible future then, Owen? If we're kind of looking ahead to where this might go, you were talking about, now we don't have to do so much by hand. That's great. The bit that I'm a lot less aware of, I think, is maybe the different evolutions that we might have on that sort of more statistical side, on the more experimental design side, and what we might then do with all of the runs that the automation is now enabling us to do. We've chatted about Bayes. Do you think that's a clear area? Where else do you think this might be going?
Yeah, so with the beige part, we really don't know where it's going to go because it's still quote unquote quite new in the field. DOE has a long history for like decades really of it being a proven success. It's kind of like a gold standard, whereas Bayesian is still being explored, let's say, but the tool is finally out there and we're just waiting to see some results coming from it. And I think that's going to give us a clearer picture of where it's headed. From what we are seeing is that it could be just another tool in the toolkit, as you mentioned, as an alternative to DOE in certain scenarios and situations. I would be interested to see where that plays into the automation bit. Can we like make a system where it kind of like self-learns and loops itself? Because Bayesian optimization kind of suggests the next run, and then the machine automatically runs it, and it just keeps on, going through that loop again and again until it finds something. And maybe it takes a lot more data, but then from the data that you've collected, you might be able to like learn something from that. So that could be an interesting avenue there.
Yeah, I think that's pretty spot on. I mean, for certain problems, I have seen some publications out there where they've done exactly that, right? They have quite painstakingly built the necessary loop of software and hardware such that then, for usually quite, constrained systems, if you like, not for the full breadth of what we might experiment with biology, because a lot of experiments are very, very involved, and I think it would be exceptionally hard to have a fully closed loop automation. But I think that this is this is certainly something that we could be looking at as a field. I think, if you think about that whole cycle, then there's two sides to it, right? There's the actual running of the experiment, but then there's that interpretation, analysis, and redesign which has to happen. And I think that both of them can be real blockers in terms of the overall iteration speed.
Yeah.
And so if you're essentially automating that selection of the next set of conditions as it works its way more and more toward the defined goals of the experiment, like you say in Bayes, then maybe this is a way of dealing with that side of the coin. And if you can have it relatively, I think it's all to do with the cost of experiment and the cost of iteration. If you have a rapid and relatively low cost, then it's almost a no-brainer, isn't it? Just set that flywheel spinning.
It's the speed of that feedback loop, isn't it? It's how quickly you can do that. It's a little bit about the whole sort of data points versus time, data points per unit of time that you can collect. So there's definitely going to be situations where it just makes much more sense to do these things in a highly parallelized fashion. And the best tools we've got for that are pretty much the ones that Fisher invented 90 years ago.
Right. So long as you have some kind of reasonable understanding of your space such that you can do it, like in a short number of iterations, I guess. I think that, certainly from what we've seen with quite a high number of different use cases now, then, with the kind of slightly more tractable, I guess, biological problems, then actually you put a very high throughput, well-designed experiment at them and you solve it in a single iteration. And I think that is then it's not even called an iteration at that point, is it? It's just an experiment. And I think, for those things where, time is absolutely critical and, you have enough, I guess, capacity to do that level of parallelization, then it seems pretty powerful.
Yeah, great. Well, thanks, Owen, for joining us on the next experiment. That's been great.
Thanks a lot, man.
Thanks for having me. It's good to see you both.